Okay, so the last module will take perhaps 45 minutes or so, is on behavioral dynamics. We've called this in the past attractor dynamics approach for the robotics community because it contrasted to the potential field approach. So the idea that the behavior is the attractor. Of course, the attractor, actually all the neurodynamics also uses attractor, so it's just a term that we use then. Behavioral dynamics would be perhaps more appropriate, but these names are more or less arbitrary. So this is where I'm starting from, right? I'm saying the Breitenberg vehicle actually is a behavioral dynamics, a thing like that. And now I'm starting with that. I'm not deriving it from this kind of sensory system. In fact, that's not how we implement these in reality, nor is that really true in the nervous system of any higher animal. I mean, even invertebrates are not really like that. They are much more complex as nervous systems. So we'll now start with that and then later think about how we can tie that up to sensory and motor systems. Yes?
In a way, I think the transfer function should shift it to the origin so that we can have the reflection of the differences in intensity and head direction.
So you think this or on top?
That one should be like shifted to the origin so that we have much
That
light.
is right, and in fact you're right. So that is this is supposed to be zero here on differences. You're right. So I should have put this axis here.
Yeah.
Yes, that's right. Good point. And that is actually true. Exactly. This is an error in this plot. Very good point. In fact, I put that recently into an article, but it's not published yet. Of course, I copied the axis from one plot to the other, and this is a real error. Very good. Yeah. Nice.
Well, just now you mentioned that like in higher creatures, the nervous system is not like directly connected from sensors to your effectors. But does this actually sort of I mean, for reflex action, like when we touch something hot, we react immediately without our brain processing any of this.
Right, exactly.
But I mean, this kind of shows that there are some sensors that connect directly to your muscle.
That is true, yes.
So can we actually say this is part of the whole thing? Or?
So it's a very interesting point you raise. So, so in terms of connectivity, all neurons are connected to the sensory and motor surface. That is, there is a path to any neuron in the brain from the sensory surface through some connectivity, and from any neuron in the brain to the motor surfaces. There is no isolated subsystem. It's almost by definition, but it's also empirically true. Breitenberg was actually one of the people who classified neurons like that. So when I say disconnected, it's not that there isn't a connection, it's maybe the connection is not effective. For instance, there are neurons in that path that are below threshold. I haven't formalized that yet. This afternoon I'll say there is a sigmoid nonlinearity that characterizes neural function. So when neurons are not sufficiently activated, they cannot transmit information. So for instance, in high nervous system, if they don't fire, then they don't have an effect. So if they're below the firing threshold, they will be off. But the connection is there, but the connection is not effective. So it's actually even a challenge of how can a subsystem become disconnected? Well, it has to be inhibited enough so that it, even though they're the connections, these connections are not effective at that moment in time. And so when I say higher nervous systems can be disconnected, it can be that a lot of essentially the activity time courses are determined by internal connectivity where there is firing, but there is some inhibition, for instance, through the basal ganglia, or actually by the basal ganglia not having disinhibited the connection, that this connectivity doesn't affect the downstream. Famous example, REM sleep, where you have a lot of cortical activity, but you don't have motor connectivity because that's inhibited. The converse is true for reflexes. That is, reflex loops are relatively short loops from sensory to motor. Often, monosynaptic reflexes exist, and a lot of them have multiple synapses, and that connection is there all the time, but usually not active. and not active because the synapse is not, or the postsynaptic neuron is not driven to firing or to a sufficient level of firing to actually have an effect. And in that sense, that circuit becomes activated if there is a stimulus of sufficient size that now brings that neuron above threshold, and then the reflex emerges. And that's a general difficulty I haven't formalized yet. The nonlinearity of the nervous system through the sigmoid, that I'm just hinting at now, is quite strong compared to the mathematical systems we typically study, polynomial functions, where the nonlinearity are just sort of soft functions. But the sigmoid is very strong, and that means that effectively the system that you're studying changes when you're bringing in or taking out a subsystem, go above or below the zero of the threshold. So for instance, when experimentalists study the sensory motor patterns, they apply stimuli, and it might happen that as they apply a certain stimulus, a whole new circuit comes in because the reflex is activated. And effectively they have to say it's a different system now, because without that reflex I was studying some couplings, and now suddenly that reflex comes in and I'm essentially just seeing that reflex loop, and the other thing is just a small modulation. And that's a general difficulty. You get that everywhere in the nervous system. If you go to higher function, it might be a question of, for instance, if you have color, suddenly the color system comes in. Previously was silent, now suddenly everything might be dominated by color, and all the effects you saw previously on motion, let's say, are now just a minor modification. A long answer. Did that cover your question? Yeah. Other questions? Yeah?
So in this diagram, you try to explain the behavior using two sensing systems,
right,
and use the derivative between them with respect to
right,
each other.
Exactly.
Like say in case one sensor is broken, the system may still work by taking derivative with respect to time, for example, the differences between two time steps, for example.
That is right, yes.
Then they may also come up with such a behavior, dynamic behavior. Like
right.
this. So, like, how can we explain it in like nature? Like, which one is better to, or should we combine both?
So first of all, this is of course a metaphor. Again, this is not a good approximation of that, of any behavior really. Here the whole logic is really based on these two picking up a difference. So if one of those was broken, this system wouldn't work. It is true, actually it's sort of generic in the nervous system, that sensors are transient detectors. So sensors, that means at the least that when there is a change in the sensory signal, the system responds more strongly than if there is, or let's say, if there's a fast change, they react more strongly than if there's a slow change. Many of them also have a sustained signal, so they're not pure transient detectors, but the transient component is very strong. In fact, if you record in visual cortex, for instance, you will find sort of stationary responses that are largely independent of the average luminance level or average contrast level that you present to this animal. And only when you make a transit on the retinal surface will you actually get a burst of activity. This is formalized in neuromorphic engineering. I don't know if any neuromorphic engineer here or knows about that? Maybe not. But there's a whole discipline in neurally inspired circuits where people try to push that to the extreme, and they call that event-based computing. That is, only when there is a change on the sensory surface will they do some computation. A technical system like that is MPEG-4. Some of you might know that. That's a system that only transmits the differences in the image. That is much more effective code and not the constant part. And so people have argued actually that's a sort of a general principle in the brain. It's not 100% true because there is also some neural signature of the average level. And it's actually critical for function. And the neuromorphic engineers are actually adding that to their circuits because they find that it's too limited to only transmit the change. So that's a whole line of thinking that's actually important, and it is also a bit of a challenge to us, always talking about attractors, if the signals are so transient in nature. If your signals are transient, how do you deal with attractors? The idea is that the attractors are changing all the time, so we have to think of the transients as being slow enough that the system can follow the attractor that the transient implies. This is, for instance, formalized in a model that we do for motion detection. Motion detection is by definition a transient thing. The motion is a change, right? But while the transient is there, you have that motion percept. So on the short term, you have a stable state. So yes, that's a whole line. I wouldn't contrast that with this left-right thing. I mean, it has its own logic. For instance, you could design with just one sensor, you could design interesting behaviors, but they wouldn't be exactly that kind of behavior. Unless you have a way of taking that one sensor and looking left-right. Maybe then if you were to use head movements, for instance, then you could perhaps design a system like that. But that will be a new system. You'd have to really design it. Maybe the other dimension of what you're asking is robustness. So I argued already intuitively about stability. That is, if you have small perturbations that are phasic. The perturbation is there, but then it disappears again. And a new perturbation comes in. All of the perturbations I assumed would be just present for a short time. And then the system would always be able to recover. By this, the perturbation, let's say, puts you here and then you return. Perturbation puts you there and you return. The other thing is perturbations that are constant. If your sensor falls off, that's a constant perturbation. That is, after some time, it's still off. That will be a structural change. And the ability to maintain function when there's a structural change is sometimes called robustness. Mathematicians call that structural stability. And what it mathematically means is that when there is that change, the function is changed, but not strongly. For instance, if this function is deformed a little, but it still has one attractor, you would say that's robust, because it still has one stable behavior, maybe a little bit off, or maybe the slope is different, but it's still okay. You see, here in this case, if one of those sensors fall off, this would disappear. So this would not be a robust system. What I will be showing you later is actually more robust simply because we have multiple sensors and they are somewhat redundant, and the dynamics will be more resistant, change less under some structural change like that, like one sensor going bad, and that would then have structural stability. In the nervous system, that's a claim that the nervous system has that sort of property, although it's rarely been proven. It's one of those things everyone finds it very plausible, but the understanding how it really works is hard. There's a whole community who works on homeostasis in neural dynamic systems. Homeostasis is sort of that thing that as you change things, the system always goes back to an operational mode. And it's quite a complicated field. It's still in work. It's not very clear yet how, if they're even universal principles, there might be a lot of tricks the nervous system uses for that. Other questions? You see, I always give long answers. Okay, good. So that's the starting point. And what I'll now do is just talk about that in more robotic terms and formalize it. The main point is this idea of behavioral variable. That is, that we need that somehow, something on this axis to understand the dynamics. We need to, in other words, characterize the state of that system relative to the environment with which it is in closed loop. That's well known in engineering. It's the need to characterize the state of the control system. And we call these variables behavioral variables, and I'll go through that. And the rest is just what I told you, intuitively formalized. So here's the robotic version of this. This is our caricature of the robotic vehicles. They are not rectangles often. They're often circular if we use this very simple picture. And the epochs and the capra that you will be using in the labs are little circular robots, sort of this size, worked on the tabletop. And we have larger ones for other purposes. And the fact that they're circular has to do with the nature of the mechanical constraints. Those of you who have a driver's license may know that cars are not like that. And that is a problem when you park them. For instance, they are not symmetrical. That is, if you got into a parking spot, it's not guaranteed you can get out of it again. Mathematically true, if you ever had that experience. And that makes it more complicated. While circular robots like that are so-called non-holonomic systems, they have only 2 degrees of freedom, that is 2 wheels, with which they can turn independently. So they can turn on the spot, would be very nice for a car. And with these 2 wheels, they can reach any location in the plane and have any orientation in the plane. So they can choose freely 3 variables, the 2D location plus the orientation, with just 2 degrees of freedom. That's called non-holonomic. And that's a whole field of study. Those sorts of things are, in some sense, simpler, and we can sort of abstract away from the mechanics than if we were to take, for instance, a robot with a steered axis, a vehicle-like robot. So that's the only reason why we use this very simplified picture. So in this picture, this green thing is the nose of the robot. So the current heading direction, if you have 2 wheels, there's 1 wheel here, 1 wheel there, then the axis in which it is moving is fixed on the robot, right? This is the axis that's orthogonal to this axis on which the wheels are mounted, and by turning the wheels differentially, it will turn on the spot. The robot I'll discuss has 5 sensors. It generally has discrete sensors, these red lines, and I'll ignore that for now. At the end of this module, I'll tell you about the sensors. For now, just say there is some way of measuring the world, and I will just assume something about that first. So the characterization of this of behavior here is just the vehicle moving around in 2D. And so moving around in 2D means giving the control signals to the 2 wheels. So in that sense, we have 2 degrees of freedom. And I'll neglect 1 and just talk about 1 degree of freedom, namely just the heading direction of that vehicle. The heading direction is controlled by giving a difference to the 2 wheels, difference in command. The average command is the forward speed of the robot along its path, and I'll just assume it's constant for now. In our actual robot models, of course, we also give some design for that, but I'll just neglect that. It can be separated out. So this vehicle is moving at constant forward speed, but by giving these differential commands, it can make any kind of change to heading direction. So this heading direction is the behavioral variable. It's actually a somewhat abstract variable, and heading direction really refers to the orientation of the robot relative to some fixed axis out in the outer world. For instance, let's say along one of these walls, that will be my fixed world axis. It will turn out that it doesn't matter, that you don't need to be calibrated, and in fact, if the calibration drifts slowly, that doesn't matter. It's just for understanding, for the mental exercise that we need that variable. You will find in the end that it's only differences in heading direction that ever matter. But the underlying behavioral variable is the heading direction. Later, that will be actually really relevant. Later, namely when we do things like memory about where something is in the world, then we will actually have to calibrate that axis. So that's the heading direction as a behavioral variable. Other behavioral variables we use in our concrete models are speed, and then similar things for arms. If you think about an arm, it's more complicated, but in the end, it's also something about the end effector motion in 3D in terms of which constraints are given to the system, and that's then translated into commands to joint angles. And there's a problem with redundant arms and so on. There's a whole field that I'm not going to cover here. So one reason why that's a good behavioral variable is that the kinds of behavioral constraints we want to give the robot can be expressed in terms of values of that behavioral variable. For instance, if we want the robot to move toward a target, that's a particular value of heading. In fact, that's a value that is independent of the robot's current heading. Right? You can rotate on the spot. The green axis would change, but this angle is constant. Right? So that's actually nicer than, or in some mathematical sense, than expressing the heading in a body frame. If I express in body frame, I would say from my nose, this angle is what I want to make 0. Then I would head toward the target. But that would be the control angle, what I have to minimize, would vary when I rotate on spot. And it would be a problem if I have multiple targets and I want to select one of those. So it makes it very economical to use this world axis. Similar for obstacles. For obstacles, I could say there is a range of heading directions that I want to avoid or not adopt, depending on the size of the vehicle, the size of the obstacle. It actually also depends on the size of the vehicle, because you have to fit on the left and on the right, a subtlety that I will gloss over for now. The other constraint for behavior variable I already anticipated, that is, it has to be something that characterizes a state of the vehicle, a behavioral state. A time course of the variable has to be a behavior, and that means it has to be enactable, more specifically controllable. That is, the connection between that variable and then the actual actuator system has to be well defined and achievable. On robots, that's delegated to components. For instance, servo motors would be control systems that can actually do positional velocity servoing. And then, of course, in the nervous system, we have muscles that are quite complex control systems, and also very intelligent control systems. And they have some challenging properties, like being very compliant, that is relatively soft compared to the kinds of speeds we want to achieve. And that is a special problem, and I'll also gloss over that for now, even though it's a topic we pursue in our research a lot. That's behavioral variable. Now, behavioral dynamics is essentially now analyzing and designing a dynamic system such that the solutions of that dynamic system generate nice behavior. Nice behavior means behavior that fulfills the constraints we want to impose on the system. So what we're doing in practice when we do this in robotics is having some principled way of expressing behavioral constraints as contributions to a dynamics. That is, sort of pieces of an equation, pieces of force. And I'll formalize that in a moment. We do very similar things in modeling human behavior. And when we model human behavior, you could think of the constraints being your experimental observation of behaviors occurring, certain values of your behavior variables being observed under certain environmental conditions. And what you want to do is design a model, a dynamical model, that generates these data as solutions. And so you have a very analogous problem. It's not called usually design, it's essentially the modeling effort that is constrained by data. And of course the data, it's not the raw data, it's actually the data abstracted into what stable states do you see under which conditions, and maybe the degree of stability, how variable they are. So here I'll discuss two kinds of behavioral constraints, attractors and repellers, targets and obstacles. So if you have that target constraint, you want to head in that direction, all you have to do is impose that the rate of change of the heading direction as a function of heading direction is a function that has a zero crossing at the direction toward the target and has a negative slope around that. The same logic I explained before, negative slope will make, if you're to the right, negative rate of change decrease, to the left, positive rate of change increase, so you're converging to that attractor. This is irrespective of the left, right, whatever that means is just within that axis here. So that will be the target direction. If you impose that force, we call that a forcelet, like a wavelet, because we typically limit the range of these forces. For obstacles, we actually, for targets, we don't limit it really formally, but this is an angular variable, right? If you're going through 180 degrees, you're heading away, and then beyond that, you're heading against towards. And what we impose usually is that this is a periodic function, so it goes back to zero and has a repeller on the backside. If not, there would be some jump in the function on the back. So if you were ever to turn away from the target because of obstacles, you would get terrible instabilities when you encounter that jump. So you need to do a sinus or cosine function with the right zero crossing for that. In the obstacle avoidance, we will actually want the range really limited, because if you have left the obstacle behind yourself, you're no longer interested in being influenced by it. So that's one contribution to the dynamics. The analogous thing for obstacle avoidance would be just its inverse, a repeller that is an invariant solution where if you're to the left, you have a negative rate of change, you go further to the left. If you're to the right, you have a positive rate of change, you go further to the right. That's how you escape from that. And that would make that you move away from that heading direction. Many of the students whom we have say, initially, when they first look in our lab class, it's kind of stupid that if you want to avoid that direction, that if you're heading right to that direction, you have zero rate of change. Shouldn't you have some, strong rate of change? Why do you go through zero? In practice, it's not a problem. In practice, there is always some noise. In fact, on our robots, we add noise, but there's sensor noise and so on that will make that if you're headed right here, the repeller moves back and forth, so you are repelled, and then you're no longer on this unstable state. So it's not really a problem that you would run into an obstacle because you're sitting exactly on this. But still, you could ask yourself, why very small rates of change when you're right at the repeller? And the answer lies in the experience of all of the students who then designed a clever system that somehow isn't like that and then found it work. It's really that if you don't do that, you have to connect the very negative rate of change on the left and the very positive in some way with the jump. And that jump will wreak havoc. That will make that somewhere sensor noise can put you a little bit to the right to get this positive turning rate. And then if you go a little bit to the left, there's some sensor noise. Go on the other side, you get a very negative turning rate. Your vehicle will make wild movements and will possibly crash. Yes?
I think if we replace the terminology, then
yes.
we can explain easily. Instead of calling it rate of change, we
yes.
just call it change.
Yes.
And then at the 0 point of the change, we have the maximum rate of change. So it makes sense.
Right. Uh-huh. I'm not sure I understand that. So where's the maximum rate of so here you think it's maximum rate of change?
Yeah. Because the slope is maximized.
Oh, so like the second derivative, for
exactly.
instance.
So we call it change.
Yeah.
This is rate of change. And we see at that
right.
point we have the maximum rate of change.
Yeah. So actually the slope is the measure of stability. And so that's the slope not in time. It's in terms of heading, right? And so when you take the derivative of the rate of change, this rate in time, the derivative with respect to heading, then that is maximal at this location. That is true. Yeah, that's an interesting argument. Let's talk about that. It's an interesting argument. I wanted to mention, I don't know if that satisfies you, but we'll talk about that. It's an interesting point. In terms of rate of change, the maxima are actually here, and this has no special meaning. Sometimes we get confused by that, because you're still being attracted. So this is just a compromise because you want to tail off. Here, when I'll say that in a moment, I think I have a slide like that. We limit the range, and as a trade-off, this highest return rate of change emerges. And in robotics, in actual implementations, you have to design that because your maximum acceleration will be limited by control stuff, and you make sure that the function isn't hitting that, so you make sure that you rescale everything to be correct. Sorry, I forgot the point I wanted to make. Well, it will come back to me. So generally, if we have these forcelets, if they're attractive or repulsive, they are characterized really by three parameters. One is where the zero crossing is, the specified value, that will be from the sensor system. The other is the strength, that's the point I want to make, the strength of repulsion or attraction. Ultimately, that's in terms of time units. In the neural dynamics, I'll discuss the exponential relaxation to the attractor, and the rate of exponential relaxation is determined by that slope. The slope is, in high dimensions, will be the eigenvalue, the negative real part of the eigenvalue. And it's intuitive. If this is very steep, you have a very fast system. That means that if you deviate from the attractor, there will be a strong rate of change, right? It will very quickly try to get back. So a very stiff system. It's very flat. It will be a less stiff system, a softer system. And if you have an instability, in fact, the slope will become zero, will become flat. That's a very, very soft system. So the strength here is one important factor, and we're thinking of the strength always in terms of time units. Relaxation time is a measure of how quickly the system reacts. We can express it in time units. And when you build robots, there are constraints from that fact, because you will have to solve the equation in time on the robot, and you will have to do that perhaps with sensor information that sets that up. So you will have to have time to measure that sensor information, compute, and that will limit the speed at which you can do all that computation, and that will limit the maximal rate of change, because it's not good to have a faster dynamics than you can numerically actually do on the robot. Then your computer doesn't catch up with the dynamics and doesn't solve it correctly. So there's a constraint for the strengths that's from that. That's a major constraint we have. Usually, the motors are not a constraint. Our vehicles can move very fast. It's computing fast enough so that we can approximate the dynamics well enough with very fast terms. That's our challenge. And then there's this range term. It's a bit less easy to formalize. We use a Gaussian often convolve with the equation to define range. Where does it really end? We make smooth functions. But it's also an empirical parameter, and that is relevant when we have different contributions and we want to limit their influence so that they're not always overlapping all of them all at the same time.
The contribution is constraint on
Contribution, exactly. There's a typo here. In fact, I could correct that one. Contribution. Thank you.
But then is the constraint, or is there similar to constraint as well?
I think I had. Yeah, you're right. Each behavior constraint is should be a contribution. I have to edit that slide. You're right. It's not clear, that sentence. Yeah, it's supposed to be that every constraint makes a contribution to the dynamics, and that's a force-led. So we're just actually summing. I think I have. No, I don't have a slide like that. For now, we're just summing all these contributions of every constraint and have a summing at the level of contributions to rate of change. So just superposing these constraints. Actually, in behavioral organization, we're doing something more sophisticated, and Matthias will talk about that tomorrow. We'll be selecting different contributions by some neurodynamics, so that they're not all added up, and that can actually improve the system. If you add a lot of constraints, then you will get this problem from potential, that the potential field approach knows about spurious attractors. If you add a lot of stuff, you could imagine then you can have problems. I can, for instance, show you a class.
Yeah, the condition where you have two attractors of opposite direction, we have the same strength that
It's exactly that problem. For instance, you could have an obstacle avoidance. This would be heading against phi. I think the green isn't so great. And then these would be terms like this, for instance, here. This would repel from that. And if you have another, let's say you have another obstacle here, it would perhaps make this term, and here they would cancel, right? The sum of these two could then, this would be the sum, and would have a flat spot here, and you could hit the obstacles there. And that you could try to avoid that by design, by making sure that the ranges are such that this doesn't happen. But you could also have a selection mechanism where, for instance, until you're here, you're just taking this one and turning this one off. And then when you're on the other side, you're taking this one and turning that one off. And there is, for instance, at large developed an approach that selects like that constraints that are relevant. So the attractor dynamics approach is also a heuristic approach. It doesn't actually guarantee that the only attractor and repeller is the right one, but it does that locally, and there are things that you can do to make it exact. It's a whole topic. We can discuss that offline. For instance, you can automatically find all attractors and then tune the parameters for them to be Right. I have something on that let me maybe get there in a little while. First illustration how bifurcations work. I'll do this with an unrealistic example. We don't really do it in practice this way, but with the attractors it's kind of more intuitive. That's how I do this with attractors. So let's first think that we have two target constraints. We know somehow there are two targets and they're close to each other. If I just add these two forcelets for the two targets, then their linear parts will overlap and the red curve results. The red curve is actually the sum of these two. And what emerges is an attractor sort of in the middle, a fused attractor, and with some quantitative differences. And that will mean the vehicle will move into sort of the average of these two directions, which might be appropriate if these targets are such that the vehicle is fatter than the target. Maybe that's a good thing. For instance, we've done some modeling that's a little bit more sophisticated than this about stochastic selection, and you find in stochastic selection exactly that phenomenon. If the targets are sufficiently close that you can foveate both of them, then you're actually doing an averaging stochastic that goes into the center of gravity of the contrast distribution around the targets. It's not, this is a simplified version of that. If, in contrast, the two targets are sufficiently apart from each other in heading direction that the vehicle cannot fit on top, then maybe you want to design this kind of dynamics where the individual contributions, this lila curve here has one attractor here, the other one has an attractor there, the red is the sum, and you see the sum has the attractors at the same spot. So they pretty much go to either this target or that target. So a very small deviation here. In between, the dynamics has a zero crossing as a continuous function, and that's essentially the repeller that makes the boundary between the two ranges of regimes of attraction. So if you're initially heading somewhere to the right of this, you will go to this attractor. If you're to the left of that, you go to that attractor. And that would translate literally into some initial heading that is either closer to this or to that target. You can imagine that varies with the strength of the targets. Maybe there are different intensities, and that could translate into different strengths, and then the boundary could shift toward the object that is more stable. Actually, the boundary shifts away from that so that you are attracted more strongly to that one. That will be details. So this will be a bistable dynamics. That is, which target you're going to depends on your initial state. If you're heading right symmetrically between those two, you would need some noise to get you into one of the basins of attraction. But other than that, you're going to then stabilize your selection decision. Will be a first example of some kind of cognition. That's what I hinted at earlier, right? And that's something that you could bring about like that. And I highlight that because it gives me an opportunity to explain this concept of bifurcation. It is now, again, if I were to parametrically change the scene, I would be connecting the region where I had just a simple attractor for small difference, and the regime where I had two attractors for a large distance, and in between them is a repeller. And somewhere there would be a critical distance where they would fuse. This would be actually only the case if the system is symmetrical. As I had hinted, if it's asymmetrical, it would be more likely that this one hits that one somewhere. That would be called a tangent bifurcation. We'll get that when we do the neurodynamics. And then this attractor would be just continuous, would be sort of slightly deformed. That would be the more generic situation if you have some asymmetry in the system. So these are, again, bifurcations under some mathematical conditions. They simple bifurcations that can occur have been classified. There are only 4 basic bifurcations. Anybody knows about bifurcation theory? Who has a little bit of background in that? Pitchfork, things like that. Have you ever heard about that? 1 or 2, 3 of you? Yeah. So I used to have a module on that where I teach that, but I found that too formal in many contexts. If it's important to you, we can sit aside and I can tell you something about that. It's a relatively advanced topic in terms of dynamical systems textbooks, but the use of it is relatively simple. There's generally it's a topic of research. So there's all kinds of complications in these systems. But simple bifurcations, that means local around one fixed point, and local in parameter around one particular value. A parameter means one particular dynamical system. When we have parameters, it's families of dynamical systems, right, that can be deformed. Our sensory information spans whole families of dynamical systems. Different sensor measures will give rise to different dynamical systems. And so we're always assuming here that as sensory conditions vary, the dynamics changes continuously in some sense, smoothly. And so bifurcations are local if they happen around one particular sensory condition and around one particular state. Mathematically, it's infinitesimal around that. And then there's some mathematical constraint about how many eigenvalues of a higher dimensional system change sign. And you can say what is generic is that only one eigenvalue changes. Everything else requires some symmetry that multiple eigenvalues move at the same time. So in some pragmatic sense, these simple bifurcations are the most typical ones that are most likely to occur. And there are only 4 of them. The pitchfork is the one I'm showing here. The tangent would be when this collides with that and just annihilate. That's the second one. Transcritical is an odd one, forget about it. And the Hopf is the one that some of you might know. The Hopf is essentially like this, but this is an oscillator rather than a fixed point. If you look at it from this side, this is how a fixed point starts to oscillate. I can discuss it with any. I decided not to have a module on oscillation. Again, it's too distracting. If anyone is in that sort of area with timing and so on, it's actually one of my favorite fields. I'll be happy to discuss that with you in a private session. So these are the 4 basic bifurcations, and so this is really useful for us, because what we do in experimental design for robots or for models is essentially describe the transition behavior. We're writing down the bifurcation that we want in terms of desired behaviors or in terms of observed behaviors. And then we're trying to classify that according to these 4, and then write down the equation that has the right bifurcation. And we choose the parameters accordingly. And I'll show you this now for obstacle avoidance. It's a little bit more complex situation, where we literally tune the parameters that the bifurcation happens at the right physical condition. And when we do that, actually in robot implementation, the system works reliably and satisfactorily. Yes?
When the conditions given, so when we have the conditions that when you sum up these two, the two models,
Yeah,
analytical models,
contributions, yeah.
And you get a repeller out of it.
Yeah.
I don't know, can we inhibit the repeller, or this have like negative consequences in practice, or?
So I mean, even the term inhibit, you mean in terms of neural inhibition, or you mean just suppress?
No, just suppress it.
Suppress,
Like,
yeah.
because there, for example, in practical, it would just cause not to stay in the middle of the 2 targets, the repeller,
Yeah.
and not to move unless you have a perturbation.
So here, later in neurodynamics, actually, we'll talk about things like that really with inhibition. Here, we don't want to get rid of the repeller. The repeller is just fine. So you have to distinguish between 2 things. One is the dynamics. That gives me a survey over all the rates of change as a function of all headings. And so then it might, so this is bistable and it has all these states and they're sitting there. But your system is, of course, in one location. Your system has this state variable, and your state variable, for instance, let's say, is this or is that or so. So it doesn't sense that. It is not affected by the repeller if it isn't close to that. If it has, for instance, gone here, it's not affected by the fact that there is that repeller sitting there. And in that sense, you want to keep that repeller around, because if there was some perturbation, for instance, if one of the targets moves very strongly, or somebody kicks that robot and changes orientation, and that would move your heading direction here, or it shifts the whole dynamics around, that where you were sitting, everything is shifted, then it's very appropriate that now you would perhaps be on the other side, because now that would be the most appropriate behavior to move to the other attractor. So we don't want to get rid of the repeller. We just don't want the system to get stuck at the repeller. So we want it to move away from that. Because it's a repeller, it's not going to get stuck there unless mathematically you would be sitting right on it. That would be this hypothetical case. It's not a real case, again, because there's always sensor noise. And once noise puts you away from it, then the repeller property pushes you away. We actually sometimes have added noise into the numerical algorithm just because sensor noise is not always reliable. It can vary in strength and sometimes can be very small. Actually, most of the time it's large and you have a problem. But by chance it can be small sometimes, and then you want to make sure that you have enough probability to switch away fast. This is called sometimes first passage time. There's a whole field of studying switching between attractors and across repellers. And you can say with noise you get a good, you get a probability distribution for first passage time that is enough away from infinite. So you get a high probability of switching within a certain time interval. Yeah? So we don't want to suppress that repeller. So I'll take you through the obstacle avoidance where we really do that. With respect to target acquisition, we don't really do it that way. We do it with fields because we want to select the target not physically but internally. But with respect to obstacle, we literally do this. So here's this example: 2 obstacles and a target. Obstacle avoidance is cheap if there's no target. But a target may push you into the obstacles. Here the target is behind the obstacles in some sense. So it pushes you toward the obstacle. And I've drawn here the case where everything is fine. These brown or ochre curves are the obstacle contributions. There's a repeller here, positive slope. Another repeller from this curve, positive slope. And then the target is this pink curve here, attractor here in the middle. I've made the slope of the target less than this positive slope of the repeller. That expresses that obstacle avoidance is stronger than target acquisition. You want to avoid obstacles more than you want to go to the target. And everything is done such that the sum, which is here black, has the same repellers. Here the 2 repellers, and there's an attractor in the middle. So everything is perfect. There's some new attractors here on the outside that are in some sense emergent, right? They come from a compromise between going to the target, which would mean going this way, negative rate of change, and being repelled from that repeller still, that is a positive rate of change. So that balance gives you a new attractor. That is essentially the attractors of going around this way or going around that way. So from this situation, the system has actually 3 paths: going straight, going this way, or going that way. And these outer ones are emergent from these dynamics. You could say an obstacle contribution is to look like it has a half attractor. If you think of an obstacle, there's a repeller here, but this is sort of half an attractor, right? If it was continuing like this, this would be an attractor. And that means sort of on the side of the obstacle, there is sort of an attraction effect to that. And that combined with something else can make a true attractor. Okay, that's the situation. That's fine because the obstacle can move, the vehicle fits between these obstacles. If they're closer, if just pushed these 4 slits in here to make them closer, then you see the same thing that we looked at for targets, for attractors now happens to obstacles. They're in the linear regime, so they are now making an average repeller. And because of the slope is much larger, they overvote here the attraction from the target. So you have just a repeller here. So inside, actually, the same bifurcation happened as I just showed, just everything switched, attractors into repellers. These attractors outside are unaffected, so you still have this attractors outside. And now you see how that's important, because that's the only way how you can get to the target. So what happens inside is that same bifurcation. It's that the repellers meet and make a repeller. In the middle was this attractor previously. And that's the same pitchfork bifurcation, except attractors and repellers are interchanged. And for those, nobody knows apparently, or only a few of you know bifurcation theory, this would be the supercritical versus subcritical form of the pitchfork, and they can be mapped onto each other by inverting the direction of time, just to map it onto the mathematics. Now, if you let time run backwards, then this would be the bifurcation we just looked at. So it's one of the four, it's still the same of the four with negative time. And these attractors outside are unaffected really by that. So again, that's the bifurcation at which the behavior changes qualitatively. And now here we could say we really want this to happen when the vehicle can no longer really pass between the obstacle and obstacles. And that's what we do when we design this, for instance, in simulation, where we have these three parameters: the range, the slope, and the position. Now, the position of the obstacle is an estimate, so that there's nothing to play with. I only have two parameters to play with: the strength and the range. And with these two parameters, we want to make sure that the bifurcation happens exactly then, when the opening is no longer enough for the robot. I have here an example. This robot, I have to explain in a second how it actually works. So this robot wants to move to this target. This little cross up there has these obstacles. It's just very stupid local algorithm, essentially implementing what I just did. And this is demonstration that we did the tuning of the parameter right. What we do in this is we make an opening of different sizes, and then we make sure by parameters tuning that the bifurcation happens when that opening is large enough for the robot to pass through. So for instance, this is still not enough. No, the robot has no global plan, so it just turns away. Pierre Mallet, who designed that robot, actually helps it to not wander too far. And then in this case, it again. So the rest, this has nothing to do with the bifurcation. The bifurcation was just this local thing. That it finds it, that's another property. And then in a moment, we'll see when it passes through. One more run. Yeah, so we opened it enough. And now it passes through. Right. And so what we've actually done in parameter tuning is always we do this in simulation. And if everything is done correctly, it will work immediately in the hardware demo. This is an implementation. I'll show you a few more videos of an implementation of just what we just looked at now. In the end, I'll tell you how we link to the sensor information. I just want to make one point about this. In this case, the robot is supposed to know the target. It's the cross here where the target is. It has no sensor information about the target. So what it does is dead reckoning. It has absolute coordinates where the target is, and it keeps estimating where it is and thus updates the direction to the target. So that's not very precise, but it demonstrates only the obstacle avoidance is connected to sensor information. So this shows the robot actually finds the target, even though it has only a local. It does this attractor dynamics, right? It has only a local plan. Here's another example of finding. Now, we block the road and it finds the other direction, but it doesn't know that, right? It's just following walls essentially, always trying to go here, being pushed away from these walls. And what I'm trying to make with that is, in some sense, global behavior can emerge from local behavior if the environment is right. So if the environment is walls with a few openings, the system will tend to find targets quite well. Conversely, if you're analyzing a nervous system and it seems to have a certain competence, doesn't necessarily mean that there is a particular module in that system that generates that competence. The competence may emerge from something simpler under appropriate conditions that support the behavior, and then the behavior may fail if these conditions are not around. So in this case, the continuity of the behavior and the continuity of these walls and therefore enables the obstacle avoidance to do something that looks like global behavior. I have a couple more of those, but maybe we don't have to look at all of those. Here, this finds its way out of that, for instance. And then another one. And this, I seem to have to click on this Oops, sorry. So this is just a demonstration that for this kind of approach, of course, there's no difference between static and dynamic obstacle avoidance. So it just always takes the sensory information it has, sets repellers, and then reacts to that. Because there's even no concept for that.
The strength of the repeller is independent of the distance.
Right, so I actually didn't explain that so far, and maybe I should explain that. I'll gloss over this, first explain that. So what I just did was somehow sort of a fudge, because the way I talked about it all the time was symbolic. There's a target and there's an obstacle, and so it knows these numbers, right? And of course, to really do that, you would have to have a object recognition system that recognizes objects as, segments them and then computes their heading direction and then repels from them. For obstacle avoidance, that's actually not really necessary. Historically, we actually did that. We had a world representation and worked off that. And a lot of obstacle avoidance algorithms assume there's a world map like that. But of course, the obstacle avoidance doesn't really need that, because it doesn't really matter if it's two objects that are close to each other or it's one object. If you can't pass between them, then it's one object for you. So you don't really want to do a segmentation in the world. All you want to do is extract this behavioral information. So what you can actually do is do a low-level implementation that is directly link sensory input to this behavioral variable. Excuse me, I need water. And this is what actually happens on this robot. We have these 5 sensors on this robot. These were these little knobs that you might have seen. They are actually ultrasound sensors, but we're using only the infrared sensor that's mounted on top. The ultrasound requires more processing. So this is actually a very simple system. It sends an infrared beam out into a direction, and it measures the infrared light that comes back. And if there's a surface close, more will come back than if there's a surface far. It's not very calibrated. If the surface is large, you will get more signal than if it's not large. If it's white, you get more signal than if it's black. So it's pretty terrible, but it already is some measure of distance. And so what we then say is that every sensor always repels from the direction in the world in which it is looking. And the repulsion strength is a function of the distance measured there. So it's no longer meaningful to talk about that as an obstacle. It's just a sort of an obstacle constraint that we get for every direction. If you think through that, the sensor in the heading direction doesn't really contribute at all. It's mounted at a fixed direction, so it's always going to repel from the heading where you currently are, and the repeller therefore sits exactly at where you currently are. At the repeller, the turning rate is 0, so its contribution is 0. Tell you, funny thing is, Estella Micho, who did that, initially didn't notice that. We just wrote out the equation and we never realized. And the top front sensor fell off, and it didn't seem to matter. And we thought, oh yeah, this sensor doesn't actually contribute. We used that sensor for something else, for speed control. So we actually have only 4 sensors that act in this particular vehicle. These 4 sensors that make the dynamics. And the additional parameter to tune now is really how quickly does the repulsive force fall off with the distance. These infrared sensors turn out to be quite short-sighted. They only see about one vehicle length. That's why this is so somewhat awkward how it drives around. So when it's longer from that surface than one vehicle length, then no longer it has no the repulsion strength goes to 0, has no obstacle there. And how quickly you increase that repulsion is then a parameter that you have to tune to get that behavior right that I was showing. So that explains perhaps how this works, right? You have these 4 sensor contributions, and with these 4, I have 2 parameters for each. You're tuning that to get the bifurcation to happen right. One can think through that more mathematically. If you do this mathematically, this is actually right. It might seem a bit arbitrary, one opening. It's actually right. I just hint at that. There's a whole lecture about that. So if you think about a circular vehicle, it can, when it collides with a surface, there will be always one sensor that is closest to that collision point. Except for one case, right? When the two sensors are exactly the same difference. So generically, one sensor is closest to the collision point. So if you make sure that the repulsive strength becomes very strong when the distance becomes very small, then one sensor will dominate, the one where you're almost colliding. And then the dynamics will be determined by just one of those repulsive forcelets, and everything's fine. So there's only one case where that is not. No, we're only interested in close to collision, right? Because that's when the constraint is important. The only case where that will be not right is when the situation is symmetrical, that is two sensors, it collides exactly between two sensors. Then two sensors have the same strength. That's the case you have to design. And that is what this bifurcation analysis does right. So it makes sure that when you're in that symmetrical situation and there are just two, so you collide exactly between two sensors, and that's what we're probing here with the surface and it heading right vertical to that surface. The left and right sensor are symmetrical. And then we make this pitchfork bifurcation, that is, we tune the parameter so that it happens exactly when the opening is large enough to exclude that case. The pitchfork is this, has the symmetry constraint. And then we have covered pretty much everything. So then from then on, everything, all other cases collapse to those cases if we get close enough. Historically, Michael Dose, a computer scientist, was very precise. He actually designed, I tell you that anecdote because I think it's kind of illustrative. So this argument is sort of asymptotic, right? Close to the collision. And it really works in practice. We never have spurious repellers. Michael Dose actually always told me only about the problems. He never told me about the successes. And he had a simulator. And he never showed me the simulator. And I don't know exactly why. It was just his personality. And then every time he came up with a problem, I came up with some solution. And then he says, I have this problem. It's really terrible. Everything doesn't work. And I ultimately wanted to see it on the simulator. And then he told me, it's not easy to show because I had a graphical interface, how to set the initial position of the robot. And apparently it was only 1 pixel, so you had to put exactly the robot in one spot. And what I had designed was a circle of obstacles of a certain radius, and if you start the robot in the middle, then there's a problem. And it's exactly that cancellation problem. And then there was exact cancellation. And of course that's totally non-generic because you would never get into a circle like that if you had that approach, right? And if the circle is a little bit narrower, then you're going to collide on one side first, and our approach works. If it's a little bit more open, then your one sensor gets closer, and the whole thing works. So you can create so the approach is not exact. There are cases where it doesn't work, but those cases are hard to reach in the real world. We have no general proof, right? So maybe one can construct a whole ensemble of cases like that. But in practice, it works very well with this local analysis. And this is, I would say, sort of a wisdom that all robotics in the meantime have, that this lower level, the reactive level, works very well almost all of the time. And that efforts to make it more exact make enormous demands on representation, on perception, modeling the world and modeling constraints. And so this is certainly very true for our approach. Good. I think I have only one last point to make. This about seeing the attractors. I should say this as a sort of an exercise. Over lunch you can think about that. This approach here that we really implemented, in some sense shouldn't work. I mean, it does work, but if you think through, there's a little bit of a puzzle here, because you could think, if you do that, every sensor repels from the direction in which it looks. that looks like this carrot and stick problem. That is, if you're turning, the sensor also turns, and so its contribution to the dynamics turns, and so this dynamical system doesn't actually do what we described it should do, because if you have a repulsive forcelet, like that. Let's say you're sitting here. This is supposed to be your direction of change. You're turning to the right, but if you're turning, the forcelet also turns. So next moment in time, it will look like this, and therefore next moment in time you have zero turning rate. So it would just stay put. It would be like the carrot and the donkey problem. If you put a carrot in front of a donkey, perhaps that works. I don't know, because the donkey perhaps has a nervous system and does something. But if you put a magnet in front of a locomotive, that doesn't work, right? You just hang a magnet in front of a locomotive with a stick that doesn't pull the locomotive along. The Germans will know this story, Jim Knopf, right? And anybody knows that, or is that a different generation? Where somebody designs a system like that. You put a magnet in front of a locomotive and it can actually fly. That doesn't work, and it works for that sort of reason. But this approach actually works. And you might want to think about why it works. We have a paper where we describe that in detail. I can say roughly the individual contribution moves like that, but the sum of the contribution doesn't move like that, because it senses the world. And in the world, these contributions will vary with the sensed input. And in the world, the obstacle stays put. And therefore, the obstacle contributions, as they shift, become weaker, and new contributions that come in become stronger. And as a result, the overall repeller doesn't move. If it were to move like that, it wouldn't work. So there's actually some work needed to understand why this way of implementing the symbolic approach works. And this is sort of an interesting message for cognition again, because if you study a nervous system and you see that a system has invariance will be that you rotate on the spot, your sensory information changes, but you can still keep in mind or still avoid the object that is always in the same location in the world. Then people would be tempted to say, oh, we have some invariant representation of that object. But this kind of approach shows that can emerge just from stuff that isn't invariant, but then the superposed effect of all the different contributions can lead to invariant. So that's a little exercise. Maybe I'll be happy to talk to you about that individually. So last point, I made a parenthesis. Last point, why is it actually possible, sort of the same quality, now that you're maybe convinced that it works, why it actually does it actually work? So if you're sitting in an attractor, why can you actually behave in an interesting way? So if you're always sitting in an attractor, it's nice for the design. That's the point I'm making on the slide, because we only need to design the attractors. We just move to the attractor, so in between we just make sure that we move fast enough to the attractor, and then we design the attractors to be with a bifurcation, right? Make sure that only the right attractors are around, much easier than potential field approach, where you have to design all the transients as well. So that's very, very desirable. Plus it also has this control theoretical property that it's stable under noise. So if you use low-level sensory information, then that's robust against that. So it's certainly very nice to have an attractor. But how is it possible to do that? And the answer to that is that, yes, it is sitting instantaneously in an attractor, but that's just an approximate picture. As you move around, the attractors and repellers move. So for instance, for this vehicle, if the target was infinitely far away and there was no obstacle, then yes, it would initially turn to the target and it would go straight forever. And that would be certainly very boring behavior. And the only reason why it doesn't do that is that as it moves around, stuff changes. The obstacles come close and maybe change in angle, and therefore their forces change, and the repellers change, and the dynamical landscapes change. I have an example here. Vehicle's initially here, target, obstacle, gives you this curve. Here's where I'm cheating with the angle, so this is not correct, but I just arrange it to be plausible, because it gets really quite confusing if you turn it around. So I'm pretending that to the right on the axis is also to the right in the world, and therefore the violet line makes the attractor at the target. The ochre or brown line makes the repeller right next to the left of it. And the sum is the green, and you see it has two attractors, one to the right, one to the left. You can go around this way or that way, right, to the target. And we're assuming it's currently in a state a little bit to the left, so it's close to the middle attractor, the green dot sort of in the middle, if you look at it, where it's heading. So a moment later, it has moved, in fact, in that direction. It will be also still somewhere here. You see, now the dynamics has really changed. The target is now closer in heading to the vehicle than the obstacle. You see, these have flipped position, and as a result, this attractor is about to disappear, so it's no longer possible to move around this way, which is plausible. And all that happens is that the vehicle just tracks this attractor here. So it is not sitting in, it is tracking an attractor. If an attractor moves slowly enough, the system is following that. It's the attractive force itself that makes sure. And that's how complex behavior emerges. If the vehicle had chosen this other route and the same thing would happen, it would actually now have to change, because this is no longer a viable attractor. That, of course, wouldn't have happened, because if it had moved around this way, we wouldn't see that dynamics. You would see some other dynamics where very likely the other attractor would become unstable, and we would now have a stable attractor on that side, right? So this is not even possible to compare. So in other words, it is possible to create interesting structured behavior while sitting in an attractor, because these attractors are actually linked to sensory input and change all the time. And therefore, complex, interesting behavior emerges if the environment that acts through these constraints is complex and interesting. Technical, practical constraint: the movement of the attractors in the state space has to be slow enough for the system to be able to track the attractors. The ability to track is determined by the stability, how steep the dynamics is, and the time scale. And that, I said earlier, is limited by the numerical update rate that allows you to approximate well a dynamical system that is a little slower than the update rate. And so in practice, the cascade is like this. You compute as fast as you can. That includes a lot of the sensory processing. These infrared sensors in these simple vehicles actually need some stabilization time. They are very bad. But in later vehicles, the main problem is vision. We do everything with vision later. Vision is very computationally expensive. It takes some time to compute that. That makes the minimum update rate, and that makes how steep we can make the dynamics, and that makes how fast we can drive. We can only drive slowly enough for that to, that tracking to happen. If the environment itself is changing dynamically, we can just deal fine with it as long as that change is slow enough. If somebody shoots a bullet at the robot, it will not be able to dodge that, right? Just because of all that whole logic. Okay, so let's close here. These are the concepts that I went through. Don't think I need to elaborate on that again. In the afternoon, we'll look at the neural dynamics as a sort of a parallel route. So this was the formalization of behavioral dynamics with a behavioral variable. There we will use a neural variable, activation. Think about what can happen in neural dynamics. Dynamical field theory will be the generalization of that. But in the end of the dynamical field theory module, I will link that again to behavioral dynamics. That is, I will then essentially ask, how can a neural dynamics with a peak of activation generate a behavioral dynamics, make an attractor? And there's one famous problem in there, a normalization problem that has a very simple solution. That will be the sort of then closing the whole story.